Hi, okay, welcome back to the tutorial. So now I would like to talk about the applications of information retrieval using policy gradient, particularly the reinforced algorithm. So this is the part of the work that I really like because it addresses the core and fundamental problem of information retrieval. As we all know, the main task of information retrieval is to rank a set of documents with respect to a given query. So this series work started from 2017. So the first two papers were published in CKR 2017, in which the authors try to formulate the problem of learning to rank as a Markov decision process, and then solve the MDP using a policy gradient. And just in this year, they published a new paper, again in CKIR, with an improved method to train the reinforcement learning algorithm. So we know it has come for a long way. So we started from TF-IDF, and then BM25, and then statistical language models. So the most recent paradigm for search engines is called learning to rank. So basically, we have a large amount of training data for the past queries where the training data could be collected, for example, from the click-through logs of a search engine. So given a query, we know what links the users have clicked, which could indicate that these web pages are relevant to the query. So given this training data, we could use some machine learning algorithms to learn a ranking model, which assigns a score to each of the document in the collection. For example, a score for each web page on the internet with respect to a given query. So the learning to rank algorithms could be categorized in several different categories, point-wise, pairwise, and list-wise. Right? But no matter which kind of learning to rank algorithms you are using, in the end, it would still try to assign a single score to a document in the large collection. And this is implicitly assuming that the relevance of a document with respect to the given query is independent from the relevance of the other documents. So this so-called independence relevance assumption is assuming that the utility of a document is independent of other documents for the query. And that is restrictive because it is not really true in practice. Although this simplifies the problem a lot. So traditionally, we just try to do the ranking of the documents for the query by scoring and sorting. So each document is going to be assigned a score from the retrieval model, and then the documents would be sorted according to that score. So this makes it difficult for you to take into account the ranking positions of documents and the dependencies among documents. The reinforcement learning algorithm really fits for the purpose because if we consider the ranking problem as a sequential decision making, then it is possible for us to take into account these factors into the ranking in a principled way. So although in the past, for example, we have models that address these problems to optimize the information retrieval metrics, for example, incorporating the diversity of the search results. But these methods are mostly ad hoc. They are specially designed for some particular retrieval scenarios. Well, in contrast, if we use reinforcement learning, it is possible for us to take into account all these different factors in a principled way. So the idea is that the Markov decision process is actually going to mimic the user's browsing behavior, by which I mean the user would normally read the search result list from the top to the bottom. So when we try to generate the search results list, we could also consider it as a sequential decision-making process. So given the candidate document set, the search engine should pick the search result one by one. So which document to select for the first position to rank 1, and then we decide which document should be selected for the second position at rank 2, and so on and so forth. So the state of the user would be updated along this process. It could naturally model the user's dynamic information need when they read through the search result list. So let's have a look at this entire ranking process. It all starts from the given new query. Right? So we imagine that there should be some variables to capture the user's state. So the initial state would be based on the query given by the user. So this reflects the user's initial information need. And then the ranker, which is based on the reinforcement learning algorithm, would make use of that state to calculate the policy. So here policy in reinforcement learning means the function that tries to map the current state, ST, to the set of actions, AT, to see which one is the most beneficial. So you can consider the policy as a probabilistic distribution over the candidate documents. So according to that policy or probabilistic distribution, we could pick the best candidate document and add it to the ranked list. So we sample one document from the candidate document set, and then that best document would be placed at the top rank. So the document ranking would be constructed one by one. So once we have added some documents to the ranked list of documents, the user would get some immediate reward. So here the reward would be calculated based on the overall retrieval performance metric that you care about. For example, if you want to optimize the retrieval metric, which combines the relevance and the diversity, there's one well-known performance metric called alpha NDCG. So here we do not use the normalized version because that would be more complicated. So here they just use the alpha DCG. The reward is the alpha DCG after we have retrieved this document minus the alpha DCG at the previous time step. So this is the increment of the performance metric generated by the current action. And if we accumulate this reward over time, then it would lead to the performance metric that we would like to optimize, which is just the alpha TCG for the top A ranked documents. Right. So given the reward, we could then use policy gradient to update the model, and the state would be changed according to the transition function. So here it's simple that we just increase the ranked list, remove the documents that have already been returned from the candidate document set, and then update the latent vector reflecting the user's state. And then we get into the iteration. So to pick the next document for rank 2, and then the next document for rank 3. So until we constructed the ranked document list. So this is one episode or trajectory when we talk about the usage of reinforcement learning. So we could model the standard ad hoc text retrieval task as the this kind of Markov decision process. Here, the state would simply be the set of candidate documents xt and the time step t. Initially, at the beginning, we have, or in other words, at the time step 0, we have the entire document collection as the candidate document set. So once we have retrieved one document using the action AT, that document picked would need to be removed from the candidate document set, and then you get into the next stage, T+1. So the reward, as I've mentioned, would depend on the performance metric that you would like to optimize. So for example, you could use the average precision for the purpose of optimizing the MAP score, or you could use the DCG or alpha DCG. So here the policy is just the determined by a softmax function, where the each document would get kind of a weight, which is determined by the model parameter setter and the query document relevance feature phi, which could include a number of these standard information retrieval features, for example, TFI, DF, and so on and so forth, that measures the match between the query and the document. And the gradient, right, is just the gradient of the policy. So here you can see that they are using this version which contains the baseline. Right. So it is, although it is perfectly fine to model the ad hoc text retrieval as MTP and make use of reinforcement learning, but the real power comes from the moment when you need to model the diversity of the search results, which is has been a challenging problem for information retrieval. So if we want to optimize not just the relevance, but also the diversity of the search results, then we would want to expand the state definition to include a latent vector h. So the ht would represent the user's perceived utility, right, from the documents that he or she has already seen. So this would help us to capture the user's dynamic information needs. Again, at the beginning, at time step 0, we have the entire document collection as the candidate document set, and the initial state of the user is calculated based on the embedding of the query. Now, so after each document is selected for the record document list, the state would need to be updated. So similar to the previous formulation, we've removed the selected document from the candidate document set and add it to the previous to the document ranking list that we have already returned to the user. And the user's state would need to be updated because if the user has already seen some of the documents, then part of the information need probably has already been addressed. So the user may want to see documents with some novel information. And the reward here, for example, we could use the again the difference of the current alpha DCG and the previous alpha DCG, so that the accumulated with time, these reward would lead to the performance metric alpha DCG, which we really would like to optimize. The policy, as we have explained, is simply a probability distribution computed using the softmax function. Here, each document would have a document embedding. This is shown as X vector here, and the this would have to be combined with the current user state HT to measure their match, and the U is a parameter matrix, and the derivation of the gradient is also straightforward, but it's too long to fit in the space here. But all these details are available in the original paper. So the key point is that compared to the previous setting, we have expanded the state variable here. So for the purpose of diversification, we would need to include the current ranked document list as part of the state, and also we need to use a latent vector to represent users' perceived utility from the preceding documents so far. Now, this graph also shows the process. We started from the query vector, and then it will be transformed into this latent state representation H0. So it would then the reinforcement learning algorithm would calculate the policy to choose the best action for the next time step, which would lead to one document XM being chosen from the candidate document set. And then you would receive some reward, and then this document would be added to the ranked document list and also removed from the candidate document list. And we update the user's state and move on to the next step, which is to pick the document for the next position in the ranked list until we have completed the list, the ranked list of documents that we need. So let's have a concrete example. Consider one of the query, which is Raffles. It is an ambiguous and multifaceted query. You could have 5 different subtopics. For example, Raffles could refer to the Raffles Hotel in Singapore, or Sir Stamford Raffles, or the raffle that you could organize for a party, and the Raffles Hotel in Dubai, or the car Raffles. So all these are different subtopics which the query could actually mean by the user. So we also have the top ranked documents according to the raw information retrieval model in the this big web document collection, CoolWeb09. So each document may contain some subtopics. And so for each document here, we have the subtopics covered by that document shown in the square bracket. So for example, document D2 would cover subtopics 3 and 5, whereas document D4 would cover only the subtopic 5. So the search results may contain redundant information if we just return, measure the relevance of each document independently, and then return them as a sorted list. So to optimize the user's experience, it would be necessary for us to consider the novelty of a document given the preceding documents in the ranked list. So the objective is to cover as many subtopics as possible with a few top ranking documents. Now look at this concrete example here. So we have, let's start from the query vector as the latent vector representing the initial state of the user. So based on that, the reinforcement learning algorithm picked the document D2 as the top ranking document. And so this document covers subtopics 3 and 5. So this document is picked because it has the highest score calculated from the policy so far. And then the document would be added to the ranked document list. So D2 would now be removed from the candidate set. And the important step is that the user state H would need to be updated. So because the subtopics 3 and 5 have already been satisfied, right? Then the user's latent state would have become different. So with the updated, so as the consequence of the action, the user state was updated to H1, the ranking score of document D4 with the covered subtopic 5 would be suppressed, would be decreased from 0.46 to 0.35 because the subtopic has already been covered by the already returned document. So the ranking scores of the other 3 documents D1, D3, and D5 would have been promoted because they contain novel information to the user. So in the next step, it turns out that document D5 would be given the highest score if we calculate the best action using the updated policy, using the policy with the updated state vector H1. And then D5 would be added to the ranked document list. And after that, the state vector would be changed to H2, which again would reflect the fact that the user would have already seen the documents covering the subtopics 3 and 5, and also 1 and 4. So the document, the subtopic 2 has not been returned to the user yet. So similarly, at step 2, the state vector H2 would capture the utility provided by D2 and D5 and making the model to select the D1 because it has the most useful information to the user, which covers a new subtopic, number 2. So in contrast, the ranking scores of the D3 and the D4, whose top subtopics had been already covered by the preceding documents, would be decreased. So this example illustrates how the Markov decision process would be able to capture the user's perceived utility of information in the ranking process, and the state of the used by the reinforcement learning algorithm would be able to generate be used to generate the diverse ranked list. So in summary, using the reinforcement learning technique for learning to rank would have several advantages compared to the standard supervised learning approach. So for ad hoc text retrieval, using reinforcement learning means that we could utilize the IR performance measures calculated at all the ranking positions as the supervision information for training. So we could use performance measures such as MAP and alpha DCG directly. And that usually means that we would be able to achieve better performances. So optimizing these IR performance measures directly on the training data without any approximation or upper bounding would usually help us to achieve the best results. So if we go further to search result diversification, then reinforcement learning provides a unified criterion, which is the additional utility the user can perceive at each time step for selecting documents at each iteration. So this provides the end-to-end learning of the diverse ranking model. There's no need of the handcrafted features. All would be just achieved by using the reinforcement learning algorithm. And this reinforcement learning algorithm could be expanded to utilize both the immediate reward and also the long-term return as the supervision information during training. It really provides the flexibility for you to manipulate the reward functions in any way that you would like to have. This also sounds good. That's the work of the first two papers, in which they use the standard reinforced algorithm. But this has some problems in training because you really want to make use of the some kind of a baseline, because the gradient estimated according to the sample document list is weighted by its absolute performance score. So, however, in information retrieval, we do not really care much about the absolute score. What really matters would be the relative order of the documents in the ranked list. So, one intuitive reason for that is because we have many different types of queries. So some queries are easy, which may have many relevant documents. So it's an information need that can be easily satisfied because so many relevant documents are available in the collection. So it's an easy job for the search engine, and we could easily get high scores. But some queries are difficult. For example, query 1 here, it only has one and only relevant document, D11. So the search engine here has actually done a very good job to identify that one and only relevant document, D11, and put it at the top of the ranked list for this query Q1. So the DCG at 5, this performance measure would be calculated as 1. But let's compare it to the other query, Q2, which is an easy query. So it has 4 relevant documents available. But the search engine failed to put the relevant document at the top of the ranked list. The first document, D21, is actually not relevant to the query. So this means that the current policy for these to generate this ranked document list for Q2 is not that good. The problem is that you would actually get a higher performance metric score because you have more relevant documents available. So DCG at 5 would be calculated as 1.95. So all in all, the performance of the optimal ranking for difficult query may actually get a lower score than the performance of a suboptimal ranking for the easy query. So because easy queries would always generate a high performance scores, then if we just use the standard reinforced algorithm blindly, then the trend ranking model would be biased towards these easy queries. So this is not what we would actually want to have. So the idea to address this problem is to use use a good baseline. For example, the average, return all the as in active critical, you use the state value. But in information retrieval, it's relatively difficult. So we would like to, what we really want to have is to focus on the relative ordering of the documents with respect to the given query. Because of this relative ordering nature of IR, we care more about the relative goodness of a document compared to the others, rather than its absolute score. And this comparison is only meaningful if we are talking about the different ranked lists for the same query. But it doesn't make much sense if we compare the document lists for different queries. Sampling a pair of document lists starting from the same state